Okay, so today's learning objective is to apply and prove the standard circle theorems concerning angles, radii, tangents, and chords, and use them to prove related results. So in this video, I'll just be talking through the proofs, and kind of in the next video, I'll go through some worked examples because to prevent the video from getting a bit too long. There's 8 proofs, and you kind of do need to know all of them. You could be asked to prove a circle theorem. So kind of, I'm not doing this just so you can have an intuition behind this. It's actually something you do need to learn. So I'll get on with it. Okay, so our first circle theorem is that the angle at the center is twice the angle at the circumference. So that's saying that this angle here, so is whatever this is twice of whatever this is. So if this angle here is x, for example, this is 2x. And if you want to prove this, so the general kind of way you prove circle theorems is you end up having to add something in. So be that a radius, which is it usually is, you have to do something in order to add kind of something in order to help kind of prove the result. So if we just kind of draw a radius in, like this. Ooh, that's a very badly drawn one. Wait, switch. Okay, so that's better drawn. So if we draw a radius in like this, if I put kind of these, that means that this length is equal to this length and equal to this length. If I actually pause the video, you might actually be able to kind of prove that the angle here is half the angle here. Using the results that we've already talked about, saying say isosceles triangles, etc., you might be able to actually kind of prove the circle theorem. So honestly, just give it a pause, see what you can do. Then say 5-10 minutes on it and see if it works out. So the way kind of to do this is because now that I've put the radius in, right, you have 3 equal lengths. So you could, for example, say that this length here is x, this length here is also x, and this length here might be y, and this length here is y as well. And that now we know because that since angles in a triangle sum to 180, so we can say we actually label this a bit even. Sorry, if we go A, B, C, and we usually label the center O. Okay, deciding it doesn't want to be labeled A, so let me turn this off. Okay. A, and then we usually label the center as O. So we can say angle AOB, let angle B. Wait, actually we don't even have to say let, we can just say AOB is equal to 180 minus 2x, because angles in a triangle sum to 180. And we can say the same thing about COB. Angle COB is equal to 180 minus 2y. I'll just put this sign here to means that we copy what's above. And if we say if we think about what this here is, right, we can say that angle AOC is equal to 360 minus this angle, this and this angle. So maybe if we label this angle, I don't know, A and B. So this is A is equal to B is equal to 360 minus A minus B, because that is so angles about a point sum to 360. So is that, and we know A minus what A and B are, which is 360 minus 180 minus 2x minus 180 minus 2y. Sorry, I'm running out of bit of space, so I'll continue on. Sorry, I just had to move it over here because I was running out of space. So 360 minus 180 minus 2x minus 180 minus 2y, which we rearrange, becomes 360 minus 180, and there's a minus here and there's a minus here, that becomes plus, right? So plus 2x minus 180 plus 2y, and 360 minus 180 is just 0, so we're left with 2x plus 2y, which is equal to 2 of x plus y, which is 2 of angle ABC. So we've proved it. Therefore, angle at center equal twice at circumference. Let me move over here. So angles in the same segment are equal. I like to maybe think about this: angles subtended by the same arc are equal. That's the other way you can think of this. That's another name. So yeah, angles subtended by the same arc, and this is the other name. So basically, the way I remember this is if you think about this arc here, right? You think about the angles that are subtended by it. So if you think about the angle that's subtended by it, there's only one angle that kind of is made with this arc. So if you look at this arc, the angle that's made with this is like that angle there. So this angle and this angle here as well is made, because kind of think of it as the angle when you have a triangle and you stick it out, and at the end of it there's going to be an arc. And because this arc is same for both of these, as this angle has this arc at the end of it, and this angle also has this arc at the end of it, these two are going to be the same. So that's the way I like to think of it. So again, here what we have to do is draw something in. So this time around we draw in, say, a center. And if we draw in a center, say like this, let me turn this smart drawing business back on. It's not too smart, but it works out most of the time. Okay, and we have that. So we have, say, drawing it here, and this is the center O, which we like to label it that. Okay, see, it decides not to draw an O. So if we call this center O, and if you think about that, you say and call this angle 2x, for example, from our previous result, if you think about if the angle at the center is twice at the circumference, if you look at this shape right here, you can see that's very much similar to this shape, but kind of this point just moved along to there. So this is 2x, this is x. And the same thing applies to this one on the right. And that comes out to x as well. So they're equal. But you'd have to kind of write this a bit more formally than this if they asked you a question like this. So you can say, let O be the center. And if we label this, say, A, B, C, and D, for example, angle, and say let angle AOD equal 2x, then angle, we don't have to write angle, sorry, then ABD, i.e. this, is equal to x, and we put angle at circumference is half the angle at center, so you reference this previous one, and you can say that, and by the same logic, angle ACD is equal to x, therefore angle ABD is equal to angle ACD, and you've got your proof. Now we have another proof to do, is that the angle in the semicircle is always 90 degrees. So we draw a semicircle, and kind of this line here is the diameter, that's what we need. However we draw it, that this is going to be 90 degrees here, whatever angle. So if we could draw it, for example, like this, and that'd be 90 degrees as well, or we could draw it like this, for example, and that'd also be 90 degrees. So you can see kind of there's kind of the intuitive way, perhaps you can just think of this as an application of this one before. If you think about the angle at the center is 180, and so the angle at the circumference is going to be half that, so that's just 90. That's one way of thinking about it. The other way might be if you draw a radius in. So the radius, these are equal lengths. We can label this x, for example, label this y. So again, we should label our kind of triangle. So we can get ABC, we call the center O. So, let angle AOB equal x, and angle COB, COB is how I like to call it, COB equal y. We know x plus y equals 180 as angles on a straight line. We kind of know that, right? So and then what we can do is, if we know that sums to 180, we know that this is also a isosceles triangle. We can call this say Z here. No, actually, let's go with A, and A, and this is B and B. We then also know that so we can also say let angle AB equal A, which equals angle OBA, so this other A, OBA, that's a very bad OBA, because of, you can say isosceles, base angles of an isosceles triangle are equal, so base angles of an isosceles, and then you can write down full, of course, are equal, and then you say the same thing with y, so then you have that equal y, and then you can say something like, x plus 2a is equal to 180. And why do we know that? Because angles in a triangle sum to 180. So a is equal to 180 minus x all over 2. You can do the same thing with y and b. So b is equal to 180 minus b all over 2. And we're looking for what a plus b equals. A plus b is equal to 180 minus x minus 180 minus b all over 2, sorry, plus 180 over 2, which is 360 minus x minus y. So this should be a y, minus x minus y all over 2. And 360 minus x, and x plus y we know is 180. So 360 minus x minus y is 360 minus x plus y over 2, which is 360 minus 180 all over 2, which is 180 divided by 2, which is just 90. And there we go, job done. We have another one as well. Angles in the cyclic quadrilateral. So the opposite angles in the cyclic quadrilateral add up to 180 degrees. So say this angle here and this angle here. So I really encourage you to pause the video and use kind of some of the techniques we've talked about so far and try to apply it to this. You're going to have to be drawing in a radius and the center. So just go ahead, try it out, see what happens. Okay, I hope you pause the video, give that a go. First step, draw in a center. Dishwash wash, center there, label it O. And then draw in a few radius. So if we're thinking about, say, this angle and this angle here, right? It makes sense, I think, to connect it to these ones. Because we're going to have to connect it to something, right? So it may as well be these ones. If we connect to this, and we're kind of cutting our angle into two, which might not be too helpful. So, sorry, I redo that a bit nicer. So if we call this angle over here, say x, and this y, and let's make sure center's in, call that O, and let's go ahead and label it. We can go A, B, C, D, so A, B, C, D, and now we have to show that x plus y is summed to 180. Well, we know that it's an isosceles triangle here. We also know that this is y, right? And this is the center. This will be 2y from our first circle theorem. And if we kind of was to draw, for example, a line through this. Sorry, that actually wasn't needed. I don't know why I did that. Let's get rid of that line. Okay. And since we know, for example, this is 2y here, by that same logic, because the angle at the center is going to be kind of twice that circumference, if we look at this one here, this is going to be over here 2x. So then, you'd have the line saying let, whatever angle equal x, y, and z, you put that in, of course, but I've just drawn it in here. And we can have, you should have that line, I'm just doing it, not writing in for brevity's sake. So we can also have 2x plus 2y is equal to 360 angles around the point. And sorry, you should also have a line saying that, angle AOC is equal to 2y because of, angles at the center of twice the circumference, and same with x. It's worthwhile, again, having that. So now you have 2x plus y equals to 360, divided by 2x plus y is equal to 180. And there you go, proved. Okay, let's move on to, we've got 4 more left, there's 8 in total. Sorry, I know it's a bit of a longer video, but we have another one. Perpendicular bisector. The perpendicular bisector from the center, bisects the chord. I.e. what we're saying is that the length of this line is equal to the length of this line, and it's going to be perpendicular as well, i.e. at 90 degrees. Again, pause the video, try it out. Let me give you a hint first, actually, though. Draw this line, draw a radius here and here. I have a feeling you haven't done it yet, so you're just watching me draw this. So go ahead and, instead of watching me draw this, go ahead, give it a go. Okay. So we can't actually use the fact that these are kind of the same length. That just because that's the answer basically. So let's try not to use that. But if we know that this is the same length as this, for example, and again, let's go ahead and label things A, O, A, B. And, they can call this maybe N. And you know what? Why did I call it N and not C? Kind of personal preference, and also because this is I guess you'd call OAB the original shape, I guess, and then just convention goes that you wouldn't label the C because you try to label things like in a clockwise manner and alphabetically. So you go O A B. You don't go, for example. This is a quick aside, by the way. Sorry. I went A B C D, right? I didn't go A B C D, right? So kind of because you have a natural way in mathematics. I guess it's conventional way of labeling things. So that's why you wouldn't go call the C here because then you go A B C, right? Oh, sorry, A C B, which is a bit weird. I mean, I know that's just a bit of convention. Like I thought I'd throw that in. So that's why I put that in. So now we know that this length is whatever, and we also know that the two triangles share this length. And if you remember our right hand RHS congruency proof, we know that this triangle is congruent to this triangle, so that they're equal, so this length is equal to this length. And you'd of course have to write that out a bit, better than this. So you'd say, sorry, we don't even need the let. We can just say that, for example, O is equal to OB. In fact, I should say, you should say OA because you're starting at OA is equal to OB, and the triangle AON and NOB share the line ON, so they do share this line. So we have that they have the same hypotenuse and the same side length. So by RHS congruency, AON is congruent to NOB, and because of that, AN is equal to NB, and then we've got the job done. Therefore, if we have it kind of at the same length, that means that each is kind of a half. So therefore, ON bisects AB. You do have to have that last line, not to think of that. Radius to a tangent. This is actually a bit of a harder one to do, so let me read that out first. The angle between a tangent and the radius is 90 degrees, so this angle here, remember what a tangent was, we talked about in the last video. This is the tangent, this is the radius, obviously starting at the center O. And what we have to remember is that what you do here is actually you don't use the proof that we've been talking about before, we use something called proof by contradiction. And the whole logic of proof by contradiction is you say, if I'm trying to prove something, right? Let me suppose the opposite is true. I'll use some sort of deductive reasoning, and I'll get to some conclusion which I can show is demonstrably false, i.e. you can show it's some sort of contradiction. And because all my reasoning was right besides my assumption, that means my assumption must be false, so the opposite is true. So let me show you how it works in this case. You say, suppose angle, and of course we do need to label things, so O, we can call this A, maybe we should call this, if this is 90 degrees, it's also 90 degrees, so let's just say that, talk about this one so it's a bit easier. OAE, suppose O angle, not E, sorry, OA, let's call this point over here B, for example. Angle OAE does not equal 90 degrees. What we know actually is that when we kind of draw a line to kind of another line, we can always make it so that we find one that is 90 degrees. So if this supposes this isn't 90 degrees, we could draw, say, another line, anywhere actually, such that it is 90 degrees. So let's say this intersects at the line at the point, C, for example. Well, not C, let's say N. Intersects at N, for example. And if it intersects at N, and let's suppose that this angle is in fact 90 degrees. So suppose, and then that isn't true. If that isn't true, then we can draw a line such that angle O and B equals 90 degrees. So the angle, the line we draw doesn't have to be exactly here. It could be, it could be down here. It could be anywhere. All we're saying that there exists such a line that is 90 degrees that we can draw from O to to a point along here, which is 90 degrees. So we're saying that ON isn't kind of, let's say this angle here we're saying is 90 degrees now. And if that's the case, we also know that if this is 90 degrees, right? If you think about a triangle, we know that if this is 90 degrees, then the kind of the side opposite the 90 degrees is always the longest, or is the the hypotenuse, which is the longest side. So that means that OA, right? Because this I've got the thing wrong. It's not ONB, it's ONA equal 90. So if ONA is 90 degrees, like this angle in here is 90 degrees, that means that OA is the longest side. So OA is longer than length ON. And we can say that something like side opposite right angle is longest. So OA must be greater than ON. If we think about another point, say E here, right? We know OE is the kind of the radius. So OE is equal to OA. Which implies that EN is less than 0, because if we want OA to be larger than, if OA is greater than ON, for example, and OE is equal to OA plus, OE plus EN, and OE is equal to OA, if we minus both sides by OA, right, we get EN is less than 0, which is a contradiction. So therefore the original assumption must be true. There we go. We have another proof to show that the tangents from a point outside the circle are equal in length. So again, what we're going to do is draw in some lines in the center. So let's draw in the center O here. Let me turn my smart drawing on, so hopefully it works. Ooh, go on, smart drawing. Okay, so again, this is the radius, so this length is equal to this length. We can't actually say that these lengths are equal yet. We're just saying that's what we need to prove. So I'm going to discard that we know that, for example. If we run from the theorem we just saw about this one here, that a radius means a tangent at 90 degrees. We know this is 90 degrees. We know this is 90 degrees. If we divide this into 2, so we know kind of the two triangles share this length. So using our RHS theorem, we know that the two triangles are congruent, and as such, this length is equal to this length. So again, you'd have to write that out as well in kind of full, I guess. So you can say, you can label this O, A, B, C, for example. And we can say OA is equal to OC as both radii. We know that's true. We know also that angle OCB is equal to angle OAB, which is equal to 90 degrees, and from the theorem above, so tangent meets radii at 90 degrees. We know that's true. And we have both share OB, therefore by RHS, that RHS congruency triangle. I'm just going to write triangle ABO and CBO are congruent. Therefore, AB is equal to AC. final proof we have is that the angle between a triangle and a tangent through one of the vertices of the triangle is equal to the angle in the alternative segment. So i.e. this angle is equal to this angle, and we can also have that this angle is equal to this angle here. And the way I kind of remember this is that you basically look at the angle you have, and then you go kind of across to here. If you look at this angle, you go across to there, for example. I used to always get the model, but I'd sometimes think that this angle would go with this. But just remember, you go kind of as you go along the line. So, you know, for example, this is on the right of this line. You continue to right along the line. So you can extend this line out if you want to. I just kind of draw this line, and that helps me remember things. So the proof of this. And as usual, we're going to draw something in. First thing you're going to do is draw a center in. So center should be somewhere here. And draw, instead of the diameter this time, we're actually drawing the radius in. So if you draw the radius in, well, not the radius, I mean, instead of the radius, we're drawing the diameter, not the other way around. Draw that in, something like that. Let's pretend we got the circle on the, properly. And then if we draw another line from this point to that there, like that, and kind of it, attaches at that point, for example. So because of this, we know a few things. We know because this is an angle within the semicircle, this angle here, that's 90 degrees. So actually, before we do that, let's go ahead and label the points. Of course, there's O. We can call this A, B, C, and point this E, for example. So we know angle ACE equal to 90 degrees. Angle in a semicircle is equal to 90, and you'd obviously write that out in form just to be a bit quicker. So this is 90 degrees, and we can call this angle here, so CA, and call this N, for example. Angle CAN is equal to, so let angle CAN equal to X. This is X. We know angle OAN equals 90 degrees because it's its radius meaning a tangent, O to A to N. Radius meets tangent at 90 degrees. 90 degrees. And we know what this angle in here is, angle OAC. Angle OAC is equal to 90 minus X, because this whole thing is 90, so this angle in here is 90 minus X. Now let's think about what this angle here is. So what this angle here is, let's just, actually instead of labeling that, let's, if we draw this a bit nicer, we know that this is X, and we've talked about how this is 90 minus X. We can think about, if the angles in a triangle add up to 180 degrees, 90 minus X plus 90 plus whatever this is equals 180. So we have, let me zoom out, made a bit more space. So angle AEC, that's going to cover go under my face. So angle AEC is equal to 180 minus 90 minus X minus 90. So angle triangle sum to 180. Of course, again, I'm being a bit quick. So the angle it's AEC is 180 minus 90 minus X minus 90. That's just X if we rearrange that. And if that's X, we know this here is also X because angles subtended by the same arc, and we've got the proof now. So this was labeled B before that. So angle ABC is equal to X, angles subtended by the same arc, or equal. So there you go, that's a proof for this last one. So we've talked through all the proofs of these 8 circle theorems. There's quite a few of them, and I guess one way is that you do have to end up almost memorizing at least the first few steps of how to get kind of the answer to these, on top of kind of memorizing what they are themselves. So this is a bit of work to do. So, and I think the best way to kind of remember these is if you actually do a bit of questions, and perhaps even if you kind of list all the ones I've set out, watch through the video, right? And to see how much you remember, just go back, list all 8 of them. There's 8, right? So it should, at least you know what you're aiming towards. So if you can list all 8 out of them and kind of perhaps even do the proofs, that'd be really good. And it would show that you've remembered it. Next video, we'll be using these circle theorems to answer some questions. But yeah, so see you guys then.